Hello viewers, in today's session we are going to discuss an important differential equation involving the Dirac delta function, right? So here we have to solve this differential equation which is y prime plus y is equal to delta of t minus 1, where the initial conditions are y of 0 is equal to 0, right? So in this class we'll learn how we can solve these type of differential equations involving the Dirac delta function using the concept of Laplace transform and the inverse Laplace transform, right? So before solving this differential equation, let us recall an important result from inverse Laplace transform, right? Because that result is going to be a very important result while solving this differential equation. So the result is the inverse Laplace transform of this function, that is e raised to minus as. F of s is given by f of t minus a multiplied with h of t minus a, right? Where this h is the famous Heaviside unit step function, right? So this result would be used while solving this differential equation. So now let us rewrite this differential equation as d by dt of y of t plus y of t, and here we have delta of t minus 1, right? So let us take the Laplace transform of both sides. So the Laplace transform is given by L, and here we have y prime of t, then we have the Laplace transform of y of t, and here we have the Laplace transform of delta of t minus 1, right? So here we are using the notation y prime of t for y prime, and for y we are writing y of t, right? Okay, so now let us use another important result from Laplace transform of derivatives, because here we have the Laplace transform of the derivative of y of t. So now the Laplace transform of f prime of t is given by s times f of s minus f of 0, right? So this is the direct result which we are going to use here. So the Laplace transform of the derivative of f of t is given by s times the Laplace transform of the function f of t minus the value of the function at 0, right? So here we have the Laplace transform of y prime of t, right? So using this result, we can now write here s times the Laplace transform of the function f of t. So here for y prime of t, we have the function y of t. So here we can write the y of s, right? So here we are using the notation capital Y of s for the Laplace transform of this function y of t, right? So the Laplace transform of y of t can be written as capital Y of s, and then we have f of 0. So for f of 0 we can write y of 0, right? So this is the term for the Laplace transform of y prime of t, and then the Laplace transform of y of t can be replaced by this notation. So here we have y of s, and here we have Laplace transform of the delta function, and we know that the Laplace transform of the function, that is delta of t minus a, is given by e raised to minus s times a, right? So here we'll write minus s, and for a we can take the value as 1, right? So here we have minus s times 1, so this is e raised to minus s. So now using this condition, that is y of 0 is equal to 0, this term is 0. So we have s times y of s minus 0 plus y of s is equal to e raised to minus s, right? So here taking y of s common from these two terms, we have y of s, and here we have s plus 1, and this is e raised to minus s. So we can now write y of s is equal to e raised to minus s over s plus 1. And remember, y of s is the Laplace transform of the function y of t. So now we can also write here the Laplace transform of the function y of t, right? So now we have obtained the Laplace transform of the function y of t as e raised to minus s over s plus 1, right? So let us now compare this expression with this one, right? Because see, from here we can write y of t as the inverse Laplace transform of this function, that is e raised to minus s over s plus 1, right? So from here we have obtained the function y of t as the inverse Laplace transform of this function. So let us rewrite this function, which is a function of s. We can write L inverse, and here we have e raised to minus s times, and here we have 1 over s plus 1, right? So now we have obtained this expression similar to this one, right? Because see, here we have L inverse, and here we have e raised to minus as f of s, right? So if we compare these two expressions, then the value of a is 1, right? So the value of a is 1, and f of s is given by 1 over s plus 1, right? So the Laplace transform of some function is f of s is equal to 1 over s plus 1. So let us find out that function whose Laplace transform is 1 over s plus 1. So now we know that the Laplace transform of the function e raised to at is given by 1 over s minus a, right? So if we take a is equal to here minus 1, then the Laplace transform of e raised to minus t is given by 1 over s minus minus 1, that is 1 over s plus 1, right? So here we have 1 over s plus 1. So it implies that this is our Laplace transform of e raised to minus t. So the function f of t is now e raised to minus t, right? So now f of s can be written as L of f of t, and f of t is e raised to minus t, right? So now this expression, that is the inverse Laplace transform of e raised to minus as f of s, is equal to the product of these two functions, right? So this expression, that is our function y of t, is now equal to f of t minus a times h of t minus a, right? And our function f of t is e raised to minus t, and the value of a is equal to 1 here, because here we have minus s times 1. So we have f of t minus 1, and here we have h of t minus 1, and f of t minus 1 can be obtained from here by replacing this t by t minus 1. So we have e raised to minus t minus 1 times h of t minus 1, where this function h of t minus 1 is the Heaviside unit step function. So now our function y of t can be written as e raised to minus t plus 1 times h of t minus 1, right? So viewers, this is the solution of this differential equation containing the Dirac delta function, right? Because the purpose of solving a differential equation is to get the function. So here our function y of t is equal to e raised to minus t plus 1 times h of t minus 1. So viewers, the required solution of this differential equation is given by this expression, and here I would like to mention one important thing, that this expression, that is f of t minus a times h of t minus a, can also be expressed like this, that is the inverse Laplace transform of e raised to minus as f of s is equal to this expression, and this expression can also be expressed like this, that is f of t minus a for t greater than a, and this inverse Laplace transform is 0 when t is less than a, right? So now using this form, we can also express our solution as y of t is equal to f of t minus a, that is f of t minus 1 for t greater than 1 and 0 for t less than 1, right? And f of t minus 1 can be written as e raised to minus t minus 1 for t greater than 1, and here we have 0 for t less than 1, right? So both these forms, that is this form and this form, both are equivalent.